In this episode, we dive into three very different frontiers of AI: how atomic fact-checking can dramatically reshape clinician trust in medical recommendations, how a contamination-resistant benchmark and reranker are pushing code search beyond simple retrieval, and how mesh field theory is rethinking physics simulation with built-in guarantees of stability and conservation. From trustworthy clinical assistance to sharper developer tools and more reliable scientific models, these papers reveal how AI is becoming not just smarter, but more precise, transparent, and physically grounded. Let's explore the first paper, abstract. This randomized controlled trial tested whether atomic fact-checking, AFC, can increase clinician trust in GPT-4 and 5, generated oncology recommendations by decomposing each recommendation into discrete, factual claims and linking each claim to the exact passage in guideline sources such as NCCN, ESMO, and ASTRO documents. Among 356 clinicians in radiology, medical oncology, and radiation oncology, who produced 7,476 trust ratings across 21 cases covering 7 cancer types, AFC outperformed recommendation-only presentation, natural language explanations, source citations, and explanation plus citation. Mean trust rose to 3.8 on a 5-point Likert scale, with AFC versus 2.89 pooled across controls, corresponding to Cohen's D equals 0.94, P is less than 1. The fraction rating the system as trustworthy increased from 26.9% to 66.5%, an absolute gain of 39.5 percentage points and a number needed to treat of 2.53. The isolated AFC component remained large even against the strongest traditional transparency condition, explanation plus citation, with D equals 0.78. Standard transparency methods showed only modest dose-response gains, with effect sizes from D equals 0.25 for explanations to D equals 0.5 for explanation plus citation. AFC effects were consistent across specialties, cancer types, and most experienced strata, with especially large effects in residents and fellows, D equals 1.41. The key result is that verifiable claim-level grounding in source guidelines produce substantially more trust than post-hoc explanations, suggesting that clinical AI interfaces may benefit more from direct verification than from explanatory text. Let's explore the second paper, Beyond Retrieval, a multitask, benchmark, and model for code search. Beyond Retrieval introduces COREB, a contamination-limited benchmark that evaluates code search as a full retrieve then re-rank pipeline rather than first-stage retrieval alone. Built from 2 timed live code bench snapshots V202602 and V202603, it uses counterfactually rewritten programming problems to reduce memorization, programmatically verified execution results to assign graded relevance, and explicit hard negatives to break the usual one relevant document setup. The benchmark spans 5,087 queries across text-to-code, code-to-text, and code-to-code in Python, Java, C++, Ruby, and Go, with 3,414 generated code candidates and 1,710 text corpus items. In experiments with 11 embedding models and 5 re-rankers, code-specialized retrievers such as C2LLM and GinaCode consistently beat larger general-purpose encoders, including an over 1-2 point overall NDCG at 10 gap between C2LLM 0, 5B, and Quen 3, EMD, 8B, while no single model dominated all tasks. Short developer-style keyword queries collapsed every model to near 0 NDCG at 10, and off-the-shelf re-rankers were highly task asymmetric, producing a 1-2 point swing between the best and worst baselines on code-to-code and negative gains on other tasks. The fine-tuned COREB re-ranker, trained with LoRa on 3, 1M examples from COREB plus CodeSearchNet, apps, CosQA, and code feedback, was the first re-ranker to deliver consistent improvements across all 3 tasks, establishing a practical 2-stage code search system. Let's explore the third paper, Mesh Field Theory Port Hamiltonian Formulation of Mesh-Based Physics. Mesh field theory, MESH-FT, reframes mesh-based continuum simulation as a topology metric separation problem and proves a local reduction theorem. If a dynamics model is local, permutation equivalent, orientation covariant, and satisfies an energy balance, passivity inequality. Then its Jacobian factorizes as JRG, where the conservative interconnection J is fixed by signed mesh incidences, and only the SPD metric, constitutive operator G, and PSD dissipation R are learnable. MeshFTNet implements this by hardwiring incidence-based coupling and training only local metric and dissipation operators, without PDE residual supervision or a predefined global Hamiltonian template. On periodic 2D plane wave benchmarks, MeshFTNet reports near zero normalized energy drift at 1.3 times 10, 4 on regular grids, and 7.2 times 10, 3 inches a higher data setting, while baselines such as MeshGraphNets reach drifts of 12 to 25.9 and HNN reaches 0.63. In physics consistency tests, it achieves wave speed error 2.0 3 times 10 2, canonical consistency 9.6 3 times 10 6, momentum error 4.89 times 10 2, and the best PDE residuals and equipartition. On the well acoustic scattering data, it closely matches wavefront curvature and reflections under discontinuous media. Out of distribution tests across frequency, resolution, and wave speed shifts show stable rollouts where several baselines diverge beyond 100 inches drift, or TSMSE. Ablations confirm the theorem. Removing orientation, breaking topology, or allowing indefinite metrics sharply worsens energy stability and momentum conservation, even when one-step MSE remains small. That's a wrap on today's AI paper highlights. Thanks for watching.